Look up at the night sky on a clear evening far from city lights. You will notice a faint, milky ribbon of light stretching across the blackness of space. For thousands of years, humanity stared at this glowing pale strip with awe and curiosity. Today, we know that this ethereal band is not just a collection of distant dust, but our cosmic home, the Milky Way Galaxy. Let us embark on an extraordinary journey, pulling back from our familiar blue planet. We rise past the atmosphere, leave our moon behind, and drift past the rocky worlds and gas giants of our solar system. As we zoom out farther, the sun shrinks to a single shining dot among billions of others. Continuing our outward trek, an astonishing structure reveals itself in all its majestic glory. We are looking at a colossal, rotating island of stars, gas, dust and dark matter spanning over 100,000 light-years across. Within this massive cosmic engine reside between 100 billion and 400 billion stars, along with countless worlds, alien landscapes, and extreme physical phenomena. Our entire solar system is merely a tiny, humble speck floating along one of its sweeping spiral arms, orbiting the distant galactic core at mind-boggling speeds. Yet, despite our minuscule size, human ingenuity and scientific curiosity have allowed us to map this swirling ocean of suns and decipher the grand laws that govern its existence. Today we will learn about the Milky Way, an incredible journey through our home galaxy, exploring its violent birth, its hidden structures, and its ultimate fate. Before we dive deep into the mysteries of our cosmic neighborhood, please feel free to like and subscribe to join us on future journeys through the universe, and leave a comment below sharing where and when you are watching this from. To understand the epic origin story of the Milky Way, we must travel back to the earliest hot and dense era that current cosmology can describe, beginning approximately 13.8 billion years ago. During the earliest stages of cosmic expansion, the universe was an intensely hot, dense, and nearly uniform soup of subatomic particles. The space expanded at an unimaginable velocity. It cooled rapidly, allowing protons, neutrons, and electrons to coalesce into the very first atomic nuclei. The early cosmos was overwhelmingly dominated by two simple chemical elements, hydrogen and helium, along with tiny traces of lithium. There were no stars, no planets, no heavy elements, and no complex structures of any kind. The cosmos was dark, silent, and expanding into an unknown abyss. However, this early universe was not entirely smooth. Microscopic quantum fluctuations present during the cosmic inflation phase created tiny variations in density throughout the expanding soup of gas. Some regions contained slightly more matter than others. Over hundreds of millions of years, the relentless force of gravity amplified these minute irregularities. The denser regions began to exert a stronger gravitational pull on their surroundings, acting as cosmic magnets that drew in surrounding hydrogen and helium gas. As gravity pulled this matter inward, vast primordial clouds of pristine gas began to collapse, forming the foundational scaffolding of what would eventually become the galaxies we observe today. Deep within these collapsing primordial clouds, the density and temperature rose to extreme levels. Eventually, the centers of these gas pockets became hot and dense enough to ignite nuclear fusion, giving birth to the very first generation of stars in the cosmos, known to astrophysicists as population 3 stars. These first-generation stars were radically different from the stars that inhabit our universe today. Because the primordial gas contained almost no elements heavier than hydrogen and helium, elements that astronomers casually group together as metals, the gas clouds could not cool down efficiently during their gravitational collapse. As a direct result, population 3 stars had to grow extraordinarily massive in order to achieve hydrostatic equilibrium, often reaching masses hundreds of times greater than our Sun. These ancient stellar giants burned with a blinding, fierce blue light. Because of their immense mass, their core pressures and temperatures were astronomically high, causing them to burn through their nuclear fuel at a hyper-accelerated rate. While a stable star like our Sun can live for 10 billion years, a massive population 3 star burned through its fuel in a mere few million years. Within their scorching nuclear furnaces, These first stars forged the very first heavy elements in the history of the universe: carbon, oxygen, nitrogen, silicon, iron, and many others. When these primordial giants exhausted their nuclear fuel, their deaths were violently catastrophic. They detonated as colossal hypernovae, blasting their newly forged heavy elements far out into the surrounding gas clouds. This process, known as cosmic chemical enrichment, forever changed the composition of the interstellar medium. The gas clouds were no longer pristine hydrogen and helium. They were now seeded with the essential building blocks for rocky planets, complex chemistry, and eventually, life itself. As these first stars lived and died, gravity continued its relentless assembly work on a far grander scale. The surrounding primordial gas clouds, along with mysterious dark matter, continued to merge and collapse into vast proto-galactic fragments. Around 13.2 billion years ago, several of these massive primordial clouds and early stellar clusters began to merge together in a specific region of space, creating the ancient core of what would become the Milky Way. The stars that formed during this secondary era from the enriched debris of population 3 stars are known as population 2 stars. These stars were metal-poor compared to modern stars, but they contained just enough heavy elements to form lower-mass, long-lived stellar bodies. Many of these ancient stellar survivors can still be observed today in the central bulge and outer halo of our galaxy, serving as living fossil records of our galaxy's infancy. However, the initial collapse of gas clouds was only the first chapter in the creation of our galactic home. The early universe was a crowded, chaotic, and violent environment where small proto-galaxies frequently crossed paths. The primary driver of the Milky Way's massive growth over billions of years was a process known as galactic cannibalism, or hierarchical merging. Our nascent galaxy was not an isolated island. It was a cosmic apex predator that grew by continuously pulling in, tearing apart and consuming smaller dwarf galaxies that orbited nearby. As small dwarf galaxies ventured too close to the growing gravitational field of the early Milky Way, powerful gravitational tidal forces began to stretch and distort them. The gravitational pull of our galaxy exerted a stronger force on the front side of the satellite galaxy than on its backside, effectively stretching the smaller galaxy into a long, thin stream of stars, gas, and dust. Over hundreds of millions of years, these dwarf galaxies were shredded completely, their stellar populations stripped away and absorbed into the growing fabric of the Milky Way. Astronomers have uncovered definitive observational proof of this ancient violent history by analysing the motions and chemical compositions of stars throughout our galaxy. One of the most significant discoveries in modern galactic archaeology was the identification of a major ancient merger event known as the Gaia-Enceladus collision, often referred to as the Gaia sausage. Approximately 10 billion years ago, a dwarf galaxy roughly the size of the small Magellanic Cloud collided head-on with the early Milky Way. The impact was so catastrophic that it radically altered the structure of our young galaxy. The energy from this collision heated and puffed up the pre-existing stellar disk of the Milky Way, scattering its older stars into a thick disk and halo, while the stars from the devoured dwarf galaxy were strewn across the inner regions of our galaxy in highly eccentric orbits. This process of galactic cannibalism did not stop in the ancient past. It continues to this day. Right now, the Milky Way is actively digesting several smaller neighbours. A prominent example is the Sagittarius dwarf spheroidal galaxy, a small satellite galaxy currently passing through the main disk of the Milky Way on the opposite side of the galactic centre from Earth. As it plunges through our galaxy, the gravitational field of the Milky Way is pulling a vast tail of stars out of Sagittarius, creating a massive structure known as the Sagittarius tidal stream that wraps around our galaxy like a cosmic ribbon. Eventually, over the next few 100 million years, the Sagittarius dwarf galaxy will be completely disrupted, its remaining stars becoming permanent members of the Milky Way's vast stellar population. Another active accretion event involves the Large and Small Magellanic Clouds, two famous dwarf galaxies visible from the southern hemisphere. These two satellite galaxies are currently undergoing their first close approach to the Milky Way. The powerful gravity of our galaxy, combined with the gravitational interaction between the two clouds themselves, has pulled out a massive stream of neutral hydrogen gas known as the Magellanic Stream. This giant ribbon of gas spans over 100 degrees across the sky and contains enough raw material to seed the formation of millions of new stars once it falls completely into the main galactic disk. Through billions of years of cosmic accretion, gas collapse, and relentless galactic cannibalism, the Milky Way steadily grew from a chaotic collection of pristine gas clouds into a majestic, highly structured island universe. The continuous influx of fresh hydrogen gas from devoured dwarf galaxies provided the raw material needed to sustain star formation over billions of years, ensuring that our galaxy remained vibrant, dynamic, and capable of birthing new generations of stars. As the gas settled into a rapidly rotating flattened disk due to the conservation of angular momentum, the conditions were finally set for the emergence of middle-aged, metal-rich stars like our Sun. Our solar system was born roughly 4.6 billion years ago out of a gas cloud enriched by countless generations of dead stars that came before it. Every atom of iron in our blood, every atom of calcium in our bones, and every atom of carbon in the air we breathe was forged inside the intense nuclear furnaces of ancient stars and distributed across space through the violent history of galactic growth. The story of the Milky Way's birth is fundamentally our own story, a long, incredible journey from the primordial hydrogen of the Big Bang to the complex living world we inhabit today. Having explored the ancient origin and violent growth of our galaxy, we must now examine its architectural framework. If we could step outside the Milky Way and look at it from a distance, we would observe a magnificent, highly organized cosmic metropolis. The structural framework of our galaxy consists of several distinct zones, each with its own unique physical properties, stellar populations, and dynamics. Among these regions, the two most prominent components visible in the optical spectrum are the central bulge and the surrounding galactic disk. Understanding how these two distinct environments function provides fundamental insights into how galaxies store, cycle, and transform matter across billions of years. At the very core of our galaxy lies the central bulge, a dense, tightly packed ellipsoid-shaped swarm of stars that glows with a distinct warm yellowish-red light. Spanning roughly 10,000 light-years across, this central hub acts as the cosmic anchor around which the entire galaxy rotates. The density of stars within the galactic bulge is vastly higher than in our local neighborhood. While the average distance between stars in the suburbs of the galaxy where Earth resides is roughly 4 light-years, stars near the center of the bulge are packed together at distances measured in light days or even light hours. If our planet were located deep within the bulge, our night sky would be illuminated by thousands of stars as bright as the full moon, rendering true night an impossibility. The stellar population of the bulge consists predominantly of population 2 stars, which are ancient, metal-poor bodies that formed during the earliest chapters of galactic history. Because these stars were created billions of years ago, the short-lived, massive blue stars among them have long since burned out and exploded as supernovae. What remain are lower-mass stars that burn their nuclear fuel at a slow, measured pace. Red giants, yellow dwarfs, and ancient stellar remnants such as white dwarfs. The dominance of these aging, low-mass stars gives the bulge its characteristic golden-red hue. Furthermore, the central bulge is not a simple spherical ball of stars. Modern astronomical observations using infrared telescopes have revealed that it possesses a prominent elongated bar structure running through its center. The Milky Way is, in fact, a barred spiral galaxy. This central bar, composed of stars and gas, extends thousands of light-years on either side of the galactic nucleus, acting as a gravitational stirrer that drives gas and dust from the outer regions into the very center, feeding nuclear processes and channeling material toward the core. Directly surrounding and extending outward from this dense central bulge is the galactic disk, a wide, flattened structure that contains the vast majority of our galaxy's visible mass, interstellar gas, and active star-forming regions. The galactic disk stretches across an astonishing distance of roughly 100,000 to 120,000 light-years, yet its thickness is remarkably small in comparison. Astronomers divide the disk into two primary components based on stellar composition, age, and thickness, the thin disk and the thick disk. The thin disk is the most energetic and visually striking region of the entire Milky Way. Measuring only about 1,000 light-years in vertical thickness, it represents a remarkably narrow band relative to its vast horizontal width. This region is rich in dense interstellar gas clouds, cold cosmic dust, and active star formation. Because gas and dust continuously settle into the central plane of the rotating disk due to gravity and angular momentum conservation, the thin disk serves as the primary factory for new suns. Within the thin disk, we find population 1 stars. Unlike the ancient stars of the central bulge, population 1 stars are young, metal-rich stellar bodies that formed from gas clouds enriched by previous generations of supernovae. These stars contain higher concentrations of heavy elements such as iron, magnesium, silicon, and oxygen, which are essential for the formation of rocky terrestrial planets like Earth and the chemical building blocks of life. The thin disk is brightened by brilliant clusters of hot, young, massive stars known as O and B-type stars. These stellar giants burn with an intense blue light and radiate tremendous amounts of ultraviolet energy. Though they live brief lives, lasting only tens of millions of years, their intense radiation illuminates the surrounding gas, creating brilliant glowing emission nebulae that light up the disk plane. Interdispersed among these luminous young stars are immense dark lanes of cosmic dust, fine grains of carbon, silicon, and ice that block visible light, creating dark, silhouetted rifts across the bright stellar background of the Milky Way when viewed from Earth. Extending above and below the thin disk is the thick disk, which reaches up to 3,000 to 4,000 light-years in vertical height. The thick disk represents a transition zone between the bustling thin disk and the sparse outer halo. It is populated by older stars that possess higher orbital velocities and broader vertical orbits, carrying them well above and below the main galactic plane. These stars are generally older than those in the thin disk, with ages ranging from 8 to 12 billion years, and they carry a lower concentration of heavy elements. The thick disk is believed to be the remnant of an early, more turbulent era when the young Milky Way suffered frequent impacts and mergers with dwarf galaxies, which gravitationally kicked many early stars out of the flat thin disk into wider, tilted orbits. Our own solar system resides within the thin disk of the Milky Way, situated approximately 27,000 light-years away from the galactic center. We live in a relatively tranquil, middle-class suburban zone of the galaxy, positioned about halfway between the central bulge and the outer edge of the disk. This location is often referred to by astrophysicists as the Galactic Habitable Zone. The Galactic Habitable Zone represents a delicate cosmic equilibrium that makes the existence of complex life possible. If our solar system were located much closer to the galactic center within the dense central bulge, Earth would be exposed to intense, lethal radiation from frequent supernova explosions, powerful gamma-ray bursts, and stellar encounters that could gravitationally disrupt the orbits of planets within our solar system. Conversely, if we were located at the extreme outer edge of the galactic disk, the interstellar gas would be severely depleted of heavy elements, meaning there would not have been enough solid matter present 4.6 billion years ago to form rocky planets like Earth in the first place. Our position within the thin disk provides us with a stable, sheltered environment. Earth orbits the Sun, and the Sun orbits the center of the Milky Way in a nearly circular path at a speed of approximately 220 kilometers per second, or roughly 500,000 miles per hour. Even at this tremendous speed, the scale of our galaxy is so colossal that it takes our solar system roughly 230 million Earth-years to complete a single orbit around the galactic core. This vast timeframe is known as a cosmic year, or galactic year. The last time our planet was in this exact position in its galactic orbit, dinosaurs were just beginning to walk the Earth, and the continents were merged into a single landmass called Pangaea. Looking across the vast expanse of the galactic disk, one realizes that it is not a static ring of matter, but a churning, evolving fluid system. The delicate interplay between gravity, rotation, magnetic fields, and thermodynamics drives gas through continuous cycles of collapse, starbirth, stellar wind expulsion, and supernova enrichment. The central bulge stands as an ancient monument to the galaxy's early, energetic birth, while the surrounding thin disk remains a vibrant, ever-changing nursery where new stars, planets, and potential biospheres are continuously brought into existence. This structural balance between the ancient central core and the dynamic surrounding disk is what allows the Milky Way to endure as a stable, long-lived host for life across billions of years. Beyond the smooth distribution of stars within the central bulge and disk lies the most visually breathtaking architecture of our cosmic home, the magnificent spiral arm structure, alongside the expansive spherical halo that envelops the entire galaxy. When viewed from above the galactic plane, the Milky Way displays sweeping, luminous tendrils of stars, gas, and glowing dust that curve gracefully away from the central bar. For decades, astronomers struggled to explain how these gigantic spiral patterns could persist over billions of years without becoming tightly wound up and destroyed. The solution to this long-standing cosmic puzzle, combined with the exploration of our galaxy's outer halo, reveals a deep interplay between orbital mechanics, gravitational wave interactions, and cosmic archaeology. To understand why the spiral arms exist, one must first confront the winding dilemma. If the spiral arms were rigid material structures made of the same stars over time, the differential rotation of the galaxy would quickly destroy them. Stars closer to the galactic core complete their orbits much faster than stars farther out in the disk. If a spiral arm were composed of a fixed line of stars, the inner portion would lap the outer portion dozens of times over the galaxy's 13 billion-year lifetime, winding the arms so tightly around the center that the distinct spiral structure would smear out into a featureless disk. Yet, across the observable universe, spiral galaxies maintain distinct, majestic arms. The breakthrough in solving this mystery came through the density wave theory, proposed by physicists C.C. Lin and Frank Hsu in the mid-1960s. Density wave theory posits that spiral arms are not fixed, rigid ribbons of material, but rather moving regions of higher gravitational density, essentially cosmic traffic jams that travel slowly through the rotating disk of stars and interstellar gas. Imagine a highway where a slow-moving construction truck causes cars behind it to tap their brakes and bunch together. As individual cars approach the slow-moving zone, they decelerate, spend more time crammed together within the congestion, and then accelerate away once they pass the obstacle. The traffic jam itself moves along the highway at a speed independent of the individual cars passing through it. In a spiral galaxy, a density wave operates in precisely the same manner. Stars and interstellar gas clouds orbit the galactic center in nearly circular paths. As these gas clouds travel through the disk, they periodically enter a region where the gravitational potential is slightly stronger, a density wave. As the gas cloud enters this region of higher density, it decelerates and compresses under the increased gravitational pressure. This gravitational compression triggers a profound transformation within the interstellar medium. Guy molecular clouds, which are cold reservoirs of hydrogen gas and cosmic dust, are squeezed together as they plough into the density wave. This shock wave causes the clouds to undergo rapid gravitational collapse, sparking intense bursts of new star formation. Thousands of new stars are born inside these high-density zones. Among these newly formed stars are extremely massive, short-lived O and B-type stars. These stellar giants burn with an intense blazing blue heat and emit vast quantities of ultraviolet light, illuminating the surrounding gas clouds and causing them to glow like cosmic neon signs as emission nebulae. Because these massive blue stars consume their nuclear fuel so rapidly, they die in violent supernova explosions after only a few tens of millions of years, before they have time to complete their orbit and exit the density wave. Consequently, the bright blue light of short-lived giant stars and glowing star nurseries always highlights the crest of the density wave, making the spiral arm stand out vividly to distant observers. Smaller, longer-lived yellow and red stars, like our Sun, survive long enough to pass straight through the density wave, exiting the traffic jam and continuing their journey through the lower density regions between the spiral arms. Thus, stars are constantly entering and leaving the spiral arms, while the spiral pattern itself endures as a persistent density wave sweeping through the galactic disk. Our Milky Way is classified specifically as a barred spiral galaxy, designated as SBBC in astronomical classification schemes. The central bar structure plays an essential role in driving and maintaining these spiral density waves. The elongated bar at our galaxy's center acts as a massive gravitational oscillator, spinning around the galactic core and creating complex orbital resonances throughout the disk. As stars and gas interact with the rotating gravitational field of the central bar, they are channeled into specific orbital pathways, feeding energy into the spiral density waves and preventing them from dissipating over cosmic time. Major observations using infrared space observatories have allowed astronomers to map the primary and secondary spiral arms of the Milky Way, despite the obscuring dust along our line of sight. Our galaxy features two primary spiral arms that originate at the tips of the central bar, the Perseus arm and the Scutum Centaurus arm. These primary arms possess the highest density of ancient stars, giant molecular clouds, and active star-forming regions. In addition to these two main structures, the Milky Way contains several secondary arms and smaller spurs, including the Sagittarius arm, the Norma arm, and the Orion Cygnus arm. Our solar system resides within the Orion Cygnus arm, a secondary spur situated between the larger Perseus and Sagittarius arms. Floating inside this local arm, our Sun orbits the galactic center at a speed that closely matches the propagation speed of the local spiral density wave, allowing our solar system to spend extended periods in the quiet, relatively safe zones between major starbursting regions. While the spiral arms define the dynamic luminous plane of the disk, the Milky Way is enveloped by a vastly larger spherical structure known as the galactic halo. Extending far above and below the galactic plane and stretching outward to distances exceeding 300,000 light-years, the halo represents the cosmic outer frontier of our galaxy. Unlike the dense, gas-rich disk, the halo is an extremely diffuse, low-density environment, almost entirely devoid of interstellar gas and active star formation. The halo is populated primarily by population 2 stars, some of the oldest known stellar objects in the universe. These stars possess highly eccentric, tilted orbits that plunge through the galactic disk at steep angles before soaring high into the dark solitude of the halo. Because these stars formed over 12 billion years ago, during the earliest phase of galactic collapse, they contain extremely low abundances of heavy elements, preserving a pristine chemical snapshot of the early universe. Embedded within this vast halo are some of the most spectacular stellar structures in the cosmos: globular clusters. Globular clusters are tightly bound, spherical swarms containing anywhere from tens of thousands to over 1 million ancient stars, packed into a region only a few dozen light-years across. Bound together by their mutual gravitational attraction, globular clusters are extraordinarily stable structures that have survived intact since the dawn of the galaxy. Over 150 globular clusters orbit the Milky Way inside its halo. Objects such as Omega Centauri and the Great Globular Cluster in Hercules serve as living stellar laboratories. The stellar densities in the cores of globular clusters are astounding. Stars are situated so close together that gravitational interactions and rare stellar collisions can occur. Because all stars within a single globular cluster formed at roughly the same time from the same initial cloud of gas, they provide astronomers with an ideal tool for measuring cosmic ages and testing theories of stellar evolution. Surrounding the stellar halo is an even larger invisible structure known as the galactic corona, or hot gas halo. This massive reservoir consists of highly ionized, ultra-hot gas at temperatures of hundreds of thousands to millions of degrees, extending hundreds of thousands of light-years into intergalactic space. Though incredibly diffuse, the total mass of gas within this cosmic corona is enormous, acting as a gravitational gas reservoir that can slowly cool and rain back down onto the galactic disk to fuel future generations of stars. Together, the sweeping spiral arms driven by density waves and the immense spherical halo housing ancient globular clusters complete the grand geometric architecture of our galaxy. The spiral arms represent the bright, dynamic engine of active creation, continuously forging new suns and planetary systems within the disk. Meanwhile, the dark, expansive halo stands as a silent cosmic vault, preserving the ancient remnants and structural history of how our galaxy first emerged from the darkness of the early universe. Deep within the innermost sanctuary of our galaxy, hidden roughly 27,000 light-years away from Earth, lies a realm of extreme gravity, blinding radiation, and absolute darkness. This is the galactic center, the dynamic pivot around which hundreds of billions of stars execute their multi-million-year orbital dance. For centuries, this enigmatic region remained completely invisible to human eyes, shrouded behind dense, impenetrable veils of interstellar dust and gas that line the plane of the Milky Way's thin disk. To human eyes observing the night sky through optical telescopes, the center of the galaxy appears as a dark, starless void stretched across the constellations Sagittarius and Scorpius. This dark rift is not an absence of stars, but rather a colossal barrier composed of fine microscopic grains of carbon, silicon, and ice mixed with cold molecular hydrogen. This cosmic soot absorbs and scatters virtually all visible light passing through it. A single photon of visible light emitted near the galactic core has less than 1 in a trillion chance of penetrating this dusty veil to reach Earth-based optical observatories. For generations, the true nature of our galaxy's center remained one of the greatest mysteries in modern astronomy. However, the mid-20th century brought a revolution in observational astrophysics. Scientists realized that while visible light is completely blocked by interstellar dust, electromagnetic radiation at different wavelengths can pass through these obstacles almost entirely unhindered. Longer wavelengths of light, such as infrared waves and radio waves, possess physical properties that allow them to slip around microscopic dust particles without being absorbed or scattered. Conversely, high-energy, short-wavelength radiation, such as X-rays and gamma rays, is so energetic that it can punch straight through the cosmic debris. By deploying sophisticated radio arrays, space-based infrared observatories, and orbiting X-ray telescopes, astronomers finally pierced the dark veil of Sagittarius. When they looked at the galactic center through these non-visible spectral windows, the dark void vanished, revealing a bustling, hyper-energetic cosmic engine. At radio wavelengths, astronomers discovered complex filaments of ionized gas, expanding supernova remnants, and intense magnetic fields winding through the galactic nucleus. In the infrared spectrum, millions of ancient red stars and massive young stellar clusters stood revealed, packed together at densities tens of thousands of times higher than in our local solar neighborhood. As astronomers zoomed closer toward the precise dynamical center of the galaxy using powerful radio telescopes, they detected a surprisingly compact, immensely bright point source of radio emissions. This mysterious object was designated Sagittarius A star. Unlike the surrounding gas clouds and stellar clusters, Sagittarius A star remained stationary at the exact center of the galaxy's rotational axis, emitting powerful radio signals from a region no larger than the size of an inner planetary orbit. The discovery of such an intensely concentrated source of energy at the exact center of the Milky Way ignited a fierce scientific quest. What was this mysterious powerhouse at the heart of our cosmic home? The definitive proof of what lay hidden within Sagittarius A star came from decades of painstaking observational work led by 2 independent astronomical teams, one at the Max Planck Institute for Extraterrestrial Physics in Germany, led by Reinhard Genzel, and the other at the University of California, Los Angeles, led by Andrea Ghez. Using the world's largest optical and infrared ground-based telescopes, equipped with cutting-edge adaptive optics technology to cancel out the blurring distortion caused by Earth's atmosphere, these scientists began tracking the individual motions of stars orbiting within the innermost light days of the galactic center. These stars, known collectively as the S-stars, execute astonishing high-speed orbits around an invisible central focus. For over 30 years, astronomers tracked these stellar bodies point by point as they carved out tight, elliptical paths through the darkness. The most famous of these stars, designated S2, completes a full orbit around the central object every 16 years. At its point of closest approach, known as periastron, S2 accelerates to mind-boggling speeds exceeding 7,000 kilometers per second, roughly 2.5% of the speed of light. It swoops past the invisible central object at a distance of merely 17 light-hours, which is about 4 times the distance from the Sun to Neptune. Using Kepler's laws of planetary motion, combined with Albert Einstein's general theory of relativity, the orbital mechanics of S2 and its neighbouring stars provided an undeniable mathematical signature. To pull a massive star like S2 through such a tight, hypervelocity trajectory, an immense gravitational force is required. By calculating the precise curvature and speed of these stellar orbits, astronomers were able to weigh the central object with extraordinary precision. The results were astonishing. Packed into a volume of space smaller than our solar system is a dark mass equivalent to 4.1 million Sun-like stars. Yet, despite possessing 4 million times the mass of our Sun, this central object emits no direct light whatsoever across any spectrum. The only physical entity known to science that can pack 4 million solar masses into such an extraordinarily small volume without collapsing into a visible star is a supermassive black hole. For their revolutionary discovery, confirming the existence of a supermassive black hole at the centre of our galaxy, Genzel and Ghez were awarded the Nobel Prize in Physics. A supermassive black hole is an object of such terrifying density and gravitational strength that its escape velocity exceeds the speed of light. At its centre lies a gravitational singularity, a point where matter is crushed to infinite density and known laws of physics break down. Surrounding this point is the event horizon, a spherical boundary marking the absolute point of no return. Anything that crosses the event horizon, whether it is gas, dust, stars, or photons of light, is forever trapped inside the black hole's gravitational grip. Despite its terrifying reputation, Sagittarius A star is currently in a relatively quiescent or dormant state compared to supermassive black holes in active distant galaxies. In active galactic nuclei, or quasars, supermassive black holes continuously devour massive quantities of gas, producing blinding jets of energy that outshine entire galaxies. In contrast, Sagittarius A star is on a starved diet. The interstellar gas surrounding the galactic core is extremely hot and diffuse, making it difficult for the black hole to efficiently pull material past its event horizon. However, Sagittarius A star is far from completely dead. As small amounts of interstellar gas, dust, and stellar winds fall toward the black hole, they do not plunge straight in. Instead, due to the conservation of angular momentum, the infalling matter spirals inward, forming a swirling, superheated disk of plasma known as an accretion disk. Friction, intense magnetic fields, and gravitational compression within this accretion disk heat the gas to tens of millions of degrees. As the ionized plasma accelerates to near light speed, it emits intense flares of X-rays and infrared radiation just outside the event horizon before disappearing forever into the black hole. In May 2022, humanity achieved another momentous breakthrough in understanding this dark heart of our galaxy. The Event Horizon Telescope Collaboration, a global network of synchronized radio telescopes spanning from Antarctica to Europe and Hawaii, released the very first direct image of Sagittarius A star. By combining data from radio dishes across the globe using a technique called Very Long Baseline Interferometry, scientists created an Earth-sized virtual telescope capable of resolving detail with unprecedented clarity. The historical image did not show the black hole itself, as no light can escape from within the event horizon. Instead, it revealed the silhouette of the black hole framed against a glowing, donut-shaped ring of superheated plasma orbiting near light speed. The dark central region, known as the shadow of the black hole, is created by the bending of light under the extreme gravitational field predicted by Einstein's equations. The size and shape of this shadow matched general relativity's predictions with extraordinary mathematical accuracy, offering direct physical, visual proof of the 4 million solar mass monster dwelling at the centre of the Milky Way. The extreme environment surrounding Sagittarius A star serves as a cosmic laboratory for testing fundamental physics and the conditions that could never be recreated in a laboratory on Earth. In 2018, as the star S2 made its ultra-close flyby past Sagittarius A star, Scientists measured two critical relativistic effects predicted by Einstein over a century ago: gravitational redshift and Schwarzschild precession. Gravitational redshift occurs when light emitted by a star trying to climb out of a deep gravitational well loses energy, shifting its spectral lines toward longer, redder wavelengths. As S2 sped past the supermassive black hole at over 20 million kilometers per hour, astronomers observed this exact reddening effect in its light. Furthermore, tracking S2's orbit revealed that its path does not form a closed ellipse, but rather traces out a rosette-shaped pattern over time, a phenomenon known as orbital precession caused by the warping of spacetime around the massive black hole. In addition to the S stars, the region surrounding Sagittarius A star harbors exotic objects known as G objects. These mysterious bodies appear as puffy dust clouds most of the time, but behave like compact stars when they pass close to the black hole. Physicists suspect that these G objects are binary star systems that were forced to merge together due to the intense gravitational tidal forces exerted by Sagittarius A star, creating bloated stellar hybrids enveloped in thick shrouds of dust. The supermassive black hole at our galaxy's center is not merely a passive gravitational drain. It is a vital cosmic regulator that has shaped the evolution of the Milky Way across billions of years. Periodically, when larger gas clouds or entire stars drift too close to Sagittarius A star, they are ripped apart by tidal forces in violent events known as tidal disruption events. These feeding frenzies blast immense bubbles of high-energy particles and gamma rays far above and below the galactic plane. Evidence of ancient feeding episodes can still be seen today in the form of the Fermi bubbles, two colossal structures of high-energy gamma-ray and X-ray emission that extend 30,000 light-years above and below the center of our galaxy, originating directly from Sagittarius A star. These ancient outbursts demonstrate that while our central supermassive black hole is quiet today, it possesses the power to reshape the large-scale architecture of the entire Milky Way when awakened. Sagittarius A star stands as a monument to extreme physics, dominating the dynamics of the immediate galactic core, while holding the ultimate secrets of space, time, and gravity within its silent, dark horizon. Having journeyed to the dark, gravitational heart of the Milky Way, we turn our gaze back to the glowing, active plane of the galactic disk. Here, an ongoing cycle of creation continues uninterrupted. Stars are not eternal. They are born, evolve across millions or billions of years, and eventually die. The engines of this cosmic rebirth are interstellar nebulae and giant molecular clouds, the expansive stellar nurseries scattered throughout the spiral arms of our galaxy. Exploring these vast regions of gas and dust reveals the intricate physical mechanisms through which the cosmos transforms raw matter into brilliant suns, planetary systems, and complex worlds. Deep within the thin disk of the Milky Way lie giant molecular clouds. These cold, ultra-dense structures span hundreds of light-years across and can hold masses equivalent to hundreds of thousands of suns. Unlike the warm, diffuse atomic gas that fills much of interstellar space, giant molecular clouds are shielded from harsh starlight by thick coatings of microscopic dust. Inside these dark, freezing sanctuaries, where temperatures plunge to near absolute zero, atoms can combine into stable molecules, predominantly molecular hydrogen, along with carbon monoxide, water vapor, and complex organic compounds. Because the temperatures within these molecular clouds are extraordinarily low, thermal pressure decreases significantly. Gravity, ever persistent, slowly gains the upper hand over the internal pressure of the gas. The birth of a stellar system begins when an external force disturbs the delicate equilibrium of a giant molecular cloud. This shock can be delivered by the passing crest of a galactic spiral density wave, the gravitational impact of a nearby passing star, or the supersonic shock wave generated by a dying star detonating in a supernova explosion. When such a shock wave compresses a portion of a giant molecular cloud past a critical threshold known as the Jeans mass, localized regions begin to undergo runaway gravitational collapse. The giant cloud fragments into smaller, dense pockets of gas, each containing the raw material required to build individual stars or multiple star systems. As one of these dense cores collapses under its own gravity, its internal pressure and temperature begin to climb rapidly. Matter from the surrounding envelope falls inward toward the center, forming a dense, warm core known as a protostar. At this early stage, the protostar is not yet a true star. It does not generate energy through nuclear fusion. Instead, it shines purely from the thermal energy released by gravitational contraction. As gas falls toward the central protostar, conservation of angular momentum forces the incoming material into a rapidly spinning flattened disk surrounding the young object, a protoplanetary disk. Within this swirling disk of gas and dust, matter begins to clump together, forming planetesimals, protoplanets, and eventually full-scale planetary systems surrounding the developing central star. For hundreds of thousands of years, the protostar continues to pull mass from its circumstellar disk, while blowing powerful collimated jets of ionized gas out from its rotational poles. These bipolar jets punch through the surrounding natal cloud, creating spectacular glowing shock structures in interstellar space known as Herbig-Haro objects. As the protostar contracts further under intense gravitational force, its core temperature reaches millions of degrees. When the core temperature breaches approximately 10 million degrees Kelvin, the speed of hydrogen nuclei becomes so immense that they overcome their mutual electrostatic repulsion, the Coulomb barrier, and fuse together into helium through the proton-proton chain reaction, or the carbon-nitrogen-oxygen cycle. This moment marks the ignition of nuclear fusion. The sudden release of tremendous nuclear energy generates an outward radiation pressure that balances the inward pull of gravity, establishing a state of hydrostatic equilibrium. The protostar officially becomes a main sequence star. The path a newly ignited star follows through its life depends almost entirely on one fundamental parameter: its initial mass. Mass dictates a star's core temperature, its fusion rate, its physical color, its luminosity, and its ultimate lifespan. The Milky Way creates stars across a vast range of masses, categorizing them into various spectral types ranging from small, cool red dwarfs to colossal, scorching blue giants. At the lowest mass end of the main sequence are red dwarfs, classified as M-type stars. These low-mass stars possess less than half the mass of our Sun, with core temperatures and pressures that burn hydrogen fuel at an exceptionally slow, conservative pace. Red dwarfs are fully convective, meaning the helium created in their cores is constantly mixed throughout the entire body of the star, while fresh hydrogen from the outer layers is continuously circulated down into the nuclear furnace. Because of this efficient mixing and slow nuclear consumption, red dwarfs do not burn through their fuel in millions or billions of years. Their lifespans are measured in trillions of years. No red dwarf born since the Big Bang has ever died of old age in the entire history of the universe. Though individually dim and invisible to the naked eye from Earth, red dwarfs represent the vast majority of all stars inhabiting the Milky Way, accounting for roughly 75% of our galaxy's total stellar population. Moving up the mass spectrum, we find intermediate yellow dwarf stars like our Sun, classified as G-type stars. With core temperatures around 15 million degrees Kelvin, a yellow dwarf converts millions of tons of hydrogen into helium every second. Stars of this class maintain hydrostatic equilibrium for roughly 10 billion years. Our Sun, currently 4.6 billion years old, is resting comfortably in the middle of its stable main sequence lifespan. When a Sun-like star eventually depletes the hydrogen fuel in its core, hydrostatic equilibrium breaks down. Without outward radiation pressure to resist gravity, the inert helium core contracts and heats up, while the outer envelope of hydrogen expands dramatically and cools, causing the star to swell into a bright red giant. Eventually, the core contracts enough for helium fusion to ignite in a rapid burst called the helium flash, forging carbon and oxygen. Once its secondary fuel is exhausted, the star sheds its outer gas layers into space, forming a glowing, colourful shell known as a planetary nebula, while leaving behind its hot, dense core as a cooling white dwarf. At the absolute extreme end of the stellar spectrum are massive blue giants and supergiants, classified as O and B-type stars. These stellar powerhouses possess masses ranging from 8 to more than 100 times the mass of our Sun. Blue giants are among the most visually radiant and physically violent objects in the galactic disk. Their core temperatures reach tens of millions of degrees, driving nuclear fusion reactions at an astonishingly extravagant rate. A blue giant shines with a blinding luminosity hundreds of thousands of times greater than our Sun, emitting massive floods of energetic ultraviolet radiation that ionize the surrounding interstellar medium for dozens of light years in every direction. Classic examples of these regions include the Orion Nebula and the Eagle Nebula, where radiation from hot young blue stars carves out immense cavities within the natal gas, illuminating iconic features like the Pillars of Creation. However, this extraordinary radiance comes at a severe cost. Because blue giants consume their internal nuclear fuel with such extreme inefficiency, they exhaust their core hydrogen supplies in a mere few million to tens of millions of years, a microscopic eye blink on cosmic timescales. When a blue giant runs out of core hydrogen, it swells into a blue or red supergiant, fusing successively heavier elements, helium, carbon, neon, oxygen and silicon, in concentric shells surrounding its core, like the layers of an onion. This rapid nuclear chain reaction inside a supergiant continues until the core is converted into iron. Because fusing iron absorbs energy rather than releasing it, the star reaches an absolute nuclear dead end. Within a fraction of a second, radiation pressure shuts off completely, and gravity causes the supergiant's multi-solar mass core to catastrophically collapse in on itself, setting the stage for one of the most energetic explosions in the universe. From the silent, cold depths of dark giant molecular clouds to the blinding, radiant fires of short-lived blue supergiants, the stellar nurseries of the Milky Way act as the engine of cosmic evolution. They process raw, primordial gases, forge heavy elements deep within nuclear furnaces, and illuminate the spiral arms with vibrant light. This continuous cycle of birth, evolution, and nucleosynthesis ensures that our galaxy remains a dynamic, evolving environment where new suns and new worlds are constantly being brought to life. While low-mass stars meet a quiet end by gently casting off their outer envelopes to form planetary nebulae, massive stars perish in catastrophic explosions that shake the surrounding interstellar medium. These dramatic stellar deaths, known as core collapse supernovae, represent some of the most violent physical events in the universe. When a supergiant star exhausts its nuclear fuel and builds a core made entirely of iron, nuclear fusion instantly ceases. Iron nuclei cannot fuse to release energy. Instead, iron fusion consumes thermal energy from the core. Without the outward push of thermal radiation pressure to counteract the relentless inward crush of gravity, hydrostatic equilibrium shatters in an instant. In less than a fraction of a second, the multi-solar mass iron core of the supergiant collapses. The gravity is so overwhelming that electrons and protons within the core are squeezed together at atomic scales, undergoing electron capture to form neutrons and releasing a massive flood of ghostly particles called neutrinos. The core collapses until it reaches nuclear density, at which point the strong nuclear force and neutron degeneracy pressure cause the core to become extraordinarily rigid. The infalling outer layers of the star, plummeting inward at a significant fraction of the speed of light, slam into this unyielding nuclear core and rebound violently outward. This violent mechanical rebound, driven by an overwhelming shockwave and fueled by the immense flux of neutrinos, tears the dying supergiant apart from the inside out. The resulting core collapse supernova blast wave expands into surrounding space at velocities exceeding 10,000 kilometers per second. During the first few weeks of the explosion, a single supernova can outshine an entire galaxy composed of hundreds of billions of stars, releasing as much energy in a matter of days as our Sun will emit over its entire 10 billion-year lifespan. Inside the extreme physical environment of a supernova shockwave, intense heat and rapid neutron bombardment drive a process known as R-process nucleosynthesis. This process instantly creates elements heavier than iron, including gold, platinum, uranium, and thorium. These heavy elements, forged in the fires of stellar destruction, are blasted far out into the interstellar medium, seeding future gas clouds with the essential ingredients required to build rocky planets and complex organic matter. What remains in the wake of this cosmic destruction depends entirely on the initial mass of the progenitor star's collapsed core. If the remaining core mass exceeds approximately 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, gravity completely overcomes all known physical forces, crushing the remnant into a stellar mass black hole. However, if the remaining core mass falls between approximately 1.4 and 3 solar masses, electron degeneracy pressure is overcome, but neutron degeneracy pressure successfully halts the gravitational collapse. The result is one of the most extreme, exotic stellar remnants known to physics: a neutron star. A neutron star packs a mass greater than our entire Sun into a smooth, ultra-dense sphere measuring only about 20 kilometers or 12 miles in diameter, roughly the size of a city. The density inside a neutron star is almost beyond human comprehension. A single teaspoon of neutron star material would weigh over 6 billion tons on Earth, equivalent to the combined weight of every human being on the planet. The surface gravity of a neutron star is so immense that if an object were dropped from a height of just 1 meter, it would impact the stellar surface at millions of miles per hour, smashing into fundamental particles. Because the original progenitor star was rotating and possessed a magnetic field prior to its collapse, the conservation of angular momentum and magnetic flux causes the resulting tiny neutron star to acquire extreme physical properties. As the star shrinks from millions of kilometers across down to a 20-kilometer sphere, its rotation rate accelerates dramatically, while its magnetic field becomes concentrated to extreme levels. Many newly formed neutron stars manifest as pulsars. A pulsar is a rapidly spinning neutron star that possesses a magnetic field trillions of times stronger than that of Earth. As the pulsar rotates, its intense magnetic field accelerates charged particles from its magnetic poles, casting 2 hyper-focused narrow beams of intense electromagnetic radiation, ranging from radio waves to X-rays and gamma rays, out into the darkness of space. Because the rotational axis of the neutron star is frequently misaligned with its magnetic axis, these twin radiation beams sweep through space like a cosmic lighthouse beam. If Earth happens to lie within the sweeping path of one of these light beams, our radio telescopes detect periodic, exceptionally precise pulses of radiation every time the beam flashes across our line of sight. Pulsar rotation periods are remarkably stable, ranging from a few seconds down to several milliseconds. Millisecond pulsars can rotate hundreds of times per second, with their surfaces spinning at a significant fraction of the speed of light. Their clock-like precision allows astrophysicists to use pulsars as natural cosmic clocks to test general relativity, measure interstellar space, and search for low-frequency gravitational waves passing through the Milky Way. Even more extreme than standard pulsars are magnetars, a rare subtype of young neutron stars that possess the most powerful magnetic fields in the known universe. A magnetar's magnetic field can reach strength levels exceeding 100 billion Tesla, roughly a quadrillion times stronger than Earth's magnetic field, and tens of thousands of times stronger than any magnet ever created by humanity. The magnetic pressure surrounding a magnetar is so immense that it physically deforms the neutron star's ultra-dense outer crust, which is composed of crystalline iron atoms locked under tremendous pressure. As the hyper-powerful magnetic fields shift and twist through the star's interior, they place immense mechanical stress on the solid outer shell. When the stress exceeds the breaking point of the iron crust, the surface cracks violently in a catastrophic event known as a starquake. When a magnetar undergoes a starquake, the sudden shift in its magnetic field releases a staggering amount of energy. The star blasts out brilliant, blinding bursts of hard X-rays and high-energy gamma rays into space. In December 2004, a giant flare from a magnetar designated SGR 1806-20, located 50,000 light-years away on the far side of the Milky Way, swept past Earth. Despite the immense distance, the gamma-ray flare was so powerful that it physically ionized the upper layers of Earth's atmosphere, saturated scientific satellite detectors, and temporarily altered radio communications across the globe. Had this magnetar flare occurred within a few hundred light-years of Earth, it would have severely damaged our planet's ozone layer. The remnants of these stellar deaths leave behind breathtaking cosmic structures across the galactic plane, known as supernova remnants. Structures like the Crab Nebula, the remnant of a supernova observed by ancient astronomers in the year 1054, and the Veil Nebula serve as expanding tombstones of dead stars. At the center of the Crab Nebula, a rapidly spinning pulsar continuously pumps high-energy wind and magnetic field energy into the surrounding gas, causing the glowing gas filaments to shine brilliantly across the spectrum. These extreme environments represent the ultimate cosmic hellscapes of our galaxy. Within these compact, dead stellar remnants, matter is forced into physical regimes where gravity, magnetism, and nuclear density reach their absolute physical limits. Yet, without these violent stellar deaths, the chemical evolution of the Milky Way would grind to a halt. The shockwaves of supernovae compress nearby gas clouds to trigger new generations of stars, while their enriched debris provides the necessary elements for future worlds. Through violent destruction, the galaxy continuously recycles its mass, ensuring that from the absolute hellfire of dead stars, new life and new worlds can ultimately emerge. As we admire the brilliant spiral arms, glowing nebulae, and high-density stellar populations that illuminate our galaxy, we are confronted with a startling realization. Everything we can see represents only a tiny fraction of what actually exists. For all its grandeur, the illuminated matter of the Milky Way, the combined light from hundreds of billions of stars, vast molecular clouds, dust lanes, and extreme stellar remnants, is merely a decorative dusting of snow resting on an immense, invisible mountain. Beneath the luminous framework of our galaxy lies a profound cosmic mystery that reshaped our fundamental understanding of physics: the existence of dark matter. The story of how human beings discovered that the Milky Way is anchored by an invisible scaffold begins with a simple application of orbital mechanics. In our own solar system, the orbital motion of planets follows the laws established by Johannes Kepler and Isaac Newton. Because the vast majority of our solar system's mass is concentrated at its center within the Sun, the gravitational pull experienced by a planet weakens rapidly as its distance from the Sun increases. Consequently, inner planets like Mercury orbit at high velocities, while distant outer planets like Neptune move at a much slower, leisurely pace. The orbital velocity decreases proportionally to the inverse square root of the distance from the mass center. When mid-20th century astronomers began measuring the orbital velocities of stars and gas clouds throughout the Milky Way, they expected to observe a similar Keplerian decline. In the inner regions of the galactic disk, where visible matter is heavily concentrated within the central bulge, orbital speeds were predicted to rise. However, once an observer moved past the main concentration of stars into the outer edges of the galactic disk, the orbital velocity of stars ought to have dropped off significantly. If the visible mass of stars, gas, and dust was all that existed, outer stars should have been moving at much lower speeds compared to stars closer to the galactic core. Instead, when pioneering astronomers such as Vera Rubin and Kent Ford conducted precise spectroscopic measurements of rotation curves in the 1970s, tracking the Doppler shifts of gas clouds and stars in spiral galaxies, including our own, they uncovered a profound anomaly. The rotation curve of the Milky Way did not drop off at all in the outer regions. Instead of slowing down, the orbital speeds of stars and neutral hydrogen gas clouds remained flat, staying high even at extreme distances from the galactic center, where visible matter drops to virtually zero. Stars residing at the distant outer boundary of the galactic disk were found to be traveling through space at roughly 200 to 250 kilometers per second, speeds nearly identical to stars orbiting much closer to the center, such as our Sun. This unexpected observation presented astrophysicists with a catastrophic theoretical paradox. According to the established laws of Newtonian gravity and general relativity, if the visible stars and gas clouds were the only source of gravitational mass in the galaxy, the outer stars were moving far too fast for the galaxy to hold on to them. At such immense orbital velocities, the outward centrifugal force experienced by these outer stars should have vastly exceeded the inward gravitational pull exerted by the visible mass of the galactic disk. Mathematically, the Milky Way should have torn itself apart billions of years ago. The outer spiral arms should have flung their stars, gas clouds, and planetesimals out into the vast emptiness of intergalactic space, leaving the galaxy fragmented and stripped of its outer structures. Yet the Milky Way remained perfectly intact, retaining its outer stars in stable, bound orbits. To resolve this paradox without discarding our fundamental theories of gravity, scientists were forced to accept a revolutionary conclusion. There must be a vast, invisible mass surrounding and penetrating the Milky Way. This unseen mass exerts an immense gravitational grip on the outer stars, providing the extra inward pull required to balance their high orbital velocities and keep the galaxy from flying apart. Because this hidden material emits no electromagnetic radiation, it does not emit, absorb, reflect, or scatter light, radio waves, infrared radiation, X-rays, or gamma rays, it was given the name dark matter. Further detailed calculations revealed the astounding scale of this invisible structure. The visible disk of stars and gas in the Milky Way is embedded within an enormous, spherical cloud of unseen material known as the dark matter halo. While the visible stellar disk of our galaxy spans roughly 100,000 to 120,000 light-years across, the dark matter halo extends far beyond this luminous boundary, stretching out to distances exceeding 600,000 to 1 million light-years into intergalactic space. In terms of mass distribution, dark matter completely dominates the Milky Way. Precise gravitational mapping indicates that dark matter accounts for approximately 85% of the total mass of our galaxy, leaving ordinary baryonic matter, everything made of atoms, including stars, planets, gas clouds, and human beings, to make up a meager 15%. The total mass of the Milky Way, when accounting for its immense dark matter halo, is estimated to be roughly 1.5 trillion times the mass of our Sun. Our luminous galaxy is essentially a tiny, bright island floating inside an ocean of dark matter. What is the fundamental nature of this invisible scaffold? This question remains one of the greatest unsolved puzzles in modern science. Through decades of experimental research and astronomical observation, physicists have systematically ruled out several candidates. Dark matter cannot simply be made of cold, dark baryonic objects, such as stray rogue planets, burnt-out white dwarfs, or stellar mass black holes, objects collectively known as massive compact halo objects, or MACHOs. Extensive gravitational microlensing surveys, which search for dark objects passing in front of distant background stars and bending their light, demonstrated that MACHOs can only account for a tiny fraction of the required dark mass. Instead, the leading hypothesis among particle physicists and cosmologists is that dark matter consists of an undiscovered species of subatomic particles known as weakly interacting massive particles, or WIMPs. These hypothetical particles would possess mass and interact via gravity, but they would be entirely immune to the electromagnetic force and the strong nuclear force. They would pass straight through solid planetary matter as if it were empty space, interacting with normal matter only through gravity and occasionally the weak nuclear force. Across the globe, scientists have constructed hypersensitive underground detectors situated miles beneath solid rock in abandoned mines, shielded from cosmic rays, in a desperate attempt to capture the rare moment when a dark matter particle collides with an atomic nucleus in normal matter. Simultaneously, particle accelerators like the Large Hadron Collider at CERN attempt to create dark matter particles in high-energy collisions, while space-based observatories search for indirect signatures of dark matter particles annihilating each other in the dense core of the galactic center. Beyond providing the extra gravitational glue needed to hold the rotating disk together today, dark matter played an absolutely indispensable role in the initial creation and evolution of the Milky Way. During the early cosmic era following the Big Bang, ordinary baryonic matter was kept hot, ionized, and uniformly distributed by its intense interactions with the overwhelming background flux of photons. Regular gas could not easily clump together to begin forming stars in galaxies because radiation pressure continuously pushed it apart. Dark matter, however, was completely immune to radiation pressure. Unhindered by light, dark matter began clumping together under its own gravity very early in cosmic history, forming vast, invisible gravitational wells throughout space. These dark matter halos served as cosmic seed pods. As the universe expanded and cooled, ordinary hydrogen and helium gas fell into the gravitational potential wells pre-formed by the dark matter halos. Inside these deep gravitational pits, the gas reached the densities necessary to cool down, collapse, ignite the first stars, and build the structural foundation of the young Milky Way. Without the invisible gravitational framework provided by dark matter, ordinary matter would have remained too diffuse to condense into complex structures, meaning our galaxy, and by extension our solar system and life itself, would never have formed. Dark matter also shapes the large-scale web-like architecture of the local universe. Filaments of dark matter bridge the space between neighboring galaxies, acting as cosmic highways along which gas and dwarf satellite galaxies travel toward the Milky Way. The gravitational pull of our dark matter halo continues to guide the trajectories of satellite galaxies, drawing them into orbits around the main galactic disk and driving the ongoing process of galactic cannibalism. As we look out into the night sky, we must appreciate the profound duality of our cosmic home. The bright, dynamic world of stars, nebulae, black holes and planets that we can see with our eyes and telescopes is merely the surface of a far grander physical reality. We reside within a vast, invisible cradle of dark matter that extends hundreds of thousands of light years into the cosmic void. This unseen halo acts as a silent guardian, its gravitational grip protecting our galactic island from being torn apart by its own relentless rotation, preserving a stable, long-lived galactic environment where stars can shine and complex life can flourish across billions of years. As we look out into the vast rotating disk of the Milky Way, framed by its sweeping spiral arms and anchored by an invisible halo of dark matter, our attention naturally shifts from stars to the worlds that orbit them. For centuries, human thinkers stared into the night sky and wondered whether our solar system was a unique cosmic anomaly or merely one of countless planetary systems scattered across the galaxy. The answer to this ancient question remained entirely in the realm of philosophy until the final decade of the 20th century, when observational technology reached a level of precision that transformed hypothetical planetary science into a vibrant empirical discipline. The quest to find exoplanets, planets orbiting stars beyond our Sun, began with a profound scientific revolution. In the early 1990s, astronomers detected the very first exoplanets around a rapidly spinning neutron star, a pulsar known as PSRB 1257+12. Shortly thereafter, in 1995, astronomers Michel Mayor and Didier Queloz made the historic discovery of 51 Pegasi b, the first confirmed exoplanet orbiting a Sun-like main-sequence star. Using the radial velocity method, which measures the subtle Doppler wobble of a star caused by the gravitational tug of an orbiting companion, scientists detected a world that completely defied pre-existing models of planetary formation. This planet was a gas giant, roughly half the mass of Jupiter, yet it orbited its host star at an astonishingly close distance, closer than Mercury orbits our Sun, completing a full year in just over 4 Earth days. This discovery introduced a brand new class of worlds previously unimaginable to science: hot Jupiters. Hot Jupiters are massive gas giants whose atmospheres are scorched to thousands of degrees by their proximity to their parent stars. Their discovery demonstrated that planetary systems could be radically different from our own, driving atmospheric migration and dynamic orbital interactions that reshaped theories of cosmic evolution. Following this initial breakthrough, space-based observatories transformed exoplanet hunting from a painstaking world-by-world effort into a statistical harvest. NASA launched the historic Kepler Space Telescope, followed later by the Transiting Exoplanet Survey Satellite, known as TESS. These observatories utilized the transit method, continuously monitoring the brightness of hundreds of thousands of stars simultaneously to detect the tiny periodic dimming of starlight that occurs when an orbiting planet passes directly in front of its host star from our vantage point. The scientific yield of these missions was staggering. Kepler revealed that planets are not rare anomalies, they are extraordinarily common across the Milky Way. On average, every star in our galaxy hosts at least one planet. Our galaxy is filled with billions of planetary systems, displaying a staggering diversity of architectures that challenge human imagination. Beyond hot Jupiters, astronomers discovered super-Earths, rocky worlds with masses larger than Earth but smaller than Neptune, which have no direct equivalent in our own solar system. They mapped mini-Neptunes, thick gas-shrouded worlds with rocky cores, as well as ocean worlds entirely covered by global liquid water oceans hundreds of miles deep. Furthermore, scientists uncovered vast populations of rogue planets, dark, lonely worlds that were gravitationally ejected from their parent systems during violent early orbital chaos. These orphan worlds now drift silently through the dark interstellar void between the stars, bound only to the galactic core. As the catalogue of confirmed exoplanets grew into the thousands, astrobiologists began focusing their search on the most compelling targets: terrestrial rocky planets orbiting within the habitable zone of their parent stars. The habitable zone, often called the Goldilocks zone, is the orbital region surrounding a star where temperatures are just right, neither too hot nor too cold, allowing liquid water to exist stably on a planet's surface under appropriate atmospheric pressure. Because liquid water is the fundamental solvent required for all known biological chemistry, finding rocky planets in the habitable zone represents the primary milestone in the search for extraterrestrial life. Determining whether a planet can host life requires evaluating a complex web of environmental conditions. The nature of the host star is critical. For instance, M-dwarf red stars, which make up the vast majority of stellar hosts in the galaxy, possess extremely long lifespans, providing trillions of years for potential biological evolution. However, young red dwarfs are notoriously violent, emitting hyperactive flares of ultraviolet and X-ray radiation that can strip away planetary atmospheres and sterilize planetary surfaces. A planet in the habitable zone of a red dwarf must possess a powerful intrinsic magnetosphere and a resilient atmosphere to survive this harsh space weather. Moreover, astrobiologists evaluate planetary characteristics such as plate tectonics, which drives the carbonate-silicate cycle that stabilizes a world's climate over geological timescales, as well as the presence of a protective magnetic field generated by a liquid metallic core. Applying these criteria to statistical models yields an astounding conclusion. There may be between 11 billion and 40 billion Earth-sized planets orbiting within the habitable zones of Sun-like and red dwarf stars across the Milky Way Galaxy alone. This astronomical realization brings humanity face to face with one of the most profound intellectual paradoxes in all of science, the Fermi Paradox. Formulated by the brilliant physicist Enrico Fermi in 1950, the paradox highlights a glaring, uncomfortable contradiction between high theoretical estimates for the existence of extraterrestrial civilizations and the complete absence of any physical evidence or contact. The logic underlying the Fermi paradox is deceptively simple, yet mathematically overwhelming. The Milky Way is roughly 13 billion years old, whereas our solar system formed only 4.6 billion years ago. Countless sun-like stars and habitable rocky planets formed billions of years before Earth even existed. If intelligent life evolved on even a microscopic fraction of these ancient worlds, some of those civilizations would have had a head start of millions or even billions of years over human technology. Even if an advanced interstellar civilization traveled at a conservative speed, a small fraction of the speed of light, it could construct self-replicating robotic probes, establish interstellar colonies, and completely map and inhabit every star system in the entire Milky Way within a few tens of millions of years. On cosmic timescales, tens of millions of years is a mere blink of an eye. Therefore, if intelligent life were common, aliens should have visited our solar system long ago, and their signals, engineering projects, or communication networks should be plainly visible throughout the galaxy today. Yet, when we scan the skies with our most sensitive radio telescopes, optical arrays, and infrared space observatories, we encounter a profound, eerie silence. Where is everybody? Over the decades, scientists, philosophers, and futurists have proposed dozens of theoretical solutions to resolve the Fermi paradox. These solutions generally fall into three broad categories: The first category suggests that intelligent life is extraordinarily rare or virtually unique to Earth. This perspective is formalized by the rare Earth hypothesis, which argues that the complex chain of astrophysical, geological, and biological events required to produce intelligent life is so improbably complex that it almost never happens. According to this view, while microbial life might be common across the galaxy, the transition from simple single-celled organisms to complex multicellular life, tool-using intelligence, and technological capability requires an improbable confluence of factors: a large stabilizing moon, a protective gas giant like Jupiter to deflect comets, ideal planetary plate tectonics, and a quiet location within the Galactic Habitable Zone. In this scenario, humanity may be the very first technological civilization to emerge in the entire Milky Way. The second category proposes the existence of a conceptual barrier known as the Great Filter. The Great Filter theory suggests that at some point along the evolutionary timeline, from cosmic dust to an interstellar species, there exists an almost impassable evolutionary wall, a hurdle so difficult that virtually no species can cross it. If the Great Filter lies in our past, it means that the emergence of life or complex intelligence is extraordinarily difficult, and we have already passed the ultimate test. However, if the Great Filter lies in our future, it implies a far darker destiny, that advanced civilizations inevitably destroy themselves through nuclear war, climate collapse, runaway artificial intelligence, or resource exhaustion shortly after acquiring technological capability, explaining why no species survives long enough to colonize the galaxy. The third category posits that intelligent civilizations are common across the galaxy, but they remain hidden, undetectable, or intentionally non-interfering. This includes hypotheses such as the zoo hypothesis, which suggests that advanced alien species are aware of Earth, but deliberately observe us from a distance without making contact, treating our planet as a protected nature reserve or cultural experiment. Other theories suggest that advanced civilizations abandon radio communications altogether, transitioning into digital existences, mega-engineering projects like Dyson spheres, or exotic communication channels that our primitive technology cannot yet detect. Alternatively, the dark forest hypothesis suggests that interstellar space is a dangerous, predatory environment where civilizations intentionally maintain absolute radio silence to avoid revealing their location to aggressive cosmic neighbors. The search for answers continues to drive modern observational astrobiology. Today, astronomers use advanced space platforms like the James Webb Space Telescope to analyze the chemical compositions of exoplanet atmospheres during transit. By measuring the spectra of light passing through an exoplanet's atmosphere, scientists search for biosignatures, gaseous markers such as oxygen, ozone, methane, and carbon dioxide existing in chemical disequilibrium that strongly suggest biological activity. Furthermore, researchers search for technosignatures, unmistakable signs of advanced technology, such as artificial light on a planet's night side, industrial chemical pollutants, or radiation leaked from massive solar collecting structures. Whether humanity ultimately discovers that the Milky Way is teeming with millions of alien civilizations, or discovers that we are completely alone in the cosmic dark, the implications are staggering. If the galaxy is full of life, it means consciousness may be a natural outcome of cosmic chemistry, and we are part of a vast galactic community. If we are truly alone, it means that our small blue planet holds the only fragile flame of technological intelligence in an island universe of 400 billion stars, placing an unimaginable responsibility on humanity's shoulders to protect our world, survive our technological adolescence, and carry the light of consciousness out into the grand spiral arms of the Milky Way. Having explored the vast inner architecture, extreme central core, and planetary diversity of the Milky Way, we now extend our perspective outward, beyond the edges of its dark matter halo. Our galaxy does not drift in absolute isolation through the cosmic void. It is embedded within a dynamic galactic neighborhood known as the Local Group. The Local Group is a gravitationally bound cluster containing more than 80 galaxies, spanning an expanse of roughly 10 million light-years across space. Within this cosmic community, the Milky Way acts as one of two dominant gravitational anchors, surrounded by a complex family of dwarf satellite galaxies and massive spiral neighbors. The most prominent immediate companions of the Milky Way are the Large Magellanic Cloud and the Small Magellanic Cloud, visible as two glowing patches of light in the southern night sky. Located approximately 160,000 and 200,000 light-years away respectively, these two irregular dwarf galaxies are our closest major galactic neighbours. For billions of years, they have been locked in a complex, energetic, gravitational dance with the Milky Way, acting as laboratory specimens for studying how large galaxies gravitationally interact with smaller satellite systems. The Large Magellanic Cloud holds roughly 1/10 the mass of the Milky Way, housing billions of stars along with hyperactive star-forming regions. Its most famous feature is the Tarantula Nebula, an immense starburst region so luminous that if it were located at the same distance from Earth as the Orion Nebula, it would cast visible shadows on our planet at night. The Small Magellanic Cloud, while smaller and less massive, is equally dynamic, containing pristine, metal-poor gas that resembles the conditions of the early universe. The gravitational relationship between the Milky Way and the Magellanic Clouds is deeply turbulent. Powerful tidal forces exerted by our galaxy's immense gravitational field continuously stretch and distort both satellite galaxies. As the Magellanic Clouds orbit each other and make close passes near the Milky Way, tidal friction strips immense ribbons of neutral hydrogen gas out of their structure. This gas has been drawn out into a colossal stream known as the Magellanic Stream, a cosmic bridge of raw hydrogen that wraps around a significant portion of the Milky Way's outer halo. Eventually, this stripped hydrogen gas will fall directly into the galactic disk of the Milky Way, replenishing our galaxy's depleted reserves and providing the essential fuel needed to trigger brand new bursts of star formation for billions of years to come. Furthermore, recent orbital data indicates that the Large Magellanic Cloud is currently making its very first close passage past our galaxy, carrying its own retinue of smaller dwarf galaxies with it, and dynamically shifting the outer gravitational halo of the Milky Way. Beyond the immediate family of satellite dwarf galaxies, the local group is dominated by two massive spiral galaxies, the Milky Way and our larger twin, the Andromeda Galaxy, also known to astronomers as Messier 31. Located approximately 2.5 million light-years from Earth, Andromeda is the largest galaxy in the local group. Spanning over 200,000 light-years across and containing an estimated 1 trillion stars, Andromeda shares a strikingly similar structural blueprint with the Milky Way, featuring a prominent central bulge, a barred spiral disk, and an expansive halo of dark matter and ancient globular clusters. Separating the Milky Way and Andromeda is the Triangulum Galaxy, or Messier 33, the third largest member of the local group. Situated roughly 3 million light-years away, Triangulum is an unbarred spiral galaxy about half the size of the Milky Way. It is gravitationally bound to Andromeda, acting as a massive satellite that orbits its larger neighbour while undergoing intense internal star formation. Together, the Milky Way, Andromeda, and Triangulum form the gravitational backbone of the local group. The entire cluster is held together by the combined gravitational pull of its dark matter halos, resisting the overall expansion of the universe. Studying this cosmic neighbourhood reveals that galaxies are not static, isolated entities, but rather social structures that continuously exchange gas, exert gravitational tides, and influence each other's evolution across billions of years. Looking ahead across deep time, the story of the Milky Way transitions from its current vibrant era into a profound but partly uncertain transformation. Our galaxy is not a perpetual motion machine. The brilliant, star-studded island we inhabit is governed by the laws of thermodynamics and gravity, directing it toward a future characterized by cosmic collisions, gas exhaustion, and ultimate structural rebirth. To understand the destiny of our home galaxy, astrophysicists trace two parallel evolutionary tracks: the internal burn-down of its nuclear fuel reserves and its possible future gravitational encounter with the Andromeda Galaxy. Over the next few billion years, the internal life cycle of the Milky Way will slowly begin to wind down. In the current epoch, interstellar gas clouds are continuously squeezed by density waves to forge new generations of stars. However, this process is fundamentally inefficient and unsustainable over infinite timescales. Every time a new generation of stars ignites, a significant portion of raw interstellar hydrogen becomes permanently locked away inside long-lived, low-mass red dwarfs, white dwarfs, neutron stars, and stellar mass black holes. While supernovae and planetary nebulae return some gas back to the interstellar medium, each stellar cycle permanently consumes a fraction of available fuel. Gradually, the cold molecular gas reserves residing within the galactic disk will become severely depleted. As raw hydrogen becomes scarce, the rate of star formation in the spiral arms will slow to a crawl and eventually cease entirely. The brilliant, short-lived O and B-type blue supergiants that currently illuminate the spiral arms will burn through their remaining fuel, detonate as final supernovae, and vanish. The galactic disk will lose its striking blue hue, fading into a dimmer reddish tone, dominated by aging yellow dwarfs, red dwarfs, and dead stellar remnants. However, long before the Milky Way completely runs out of gas, a possible close encounter with the Andromeda Galaxy could profoundly reshape its structure. At this very moment, the Milky Way and the Andromeda Galaxy are rushing toward each other across the cosmic void at a speed of approximately 110 kilometers per second, or roughly 250,000 miles per hour. Driven by their mutual gravitational attraction and anchored by their immense, overlapping dark matter halos, the two giant galaxies are moving toward one another. However, uncertainties in Andromeda's transverse motion, along with the gravitational influence of nearby satellite galaxies, mean that a direct collision is not mathematically certain. If a merger occurs, the encounter could unfold over several distinct phases across billions of years. In one merger scenario, Andromeda could make an ultra-close approach to the Milky Way several billion years from now. If the outer dark matter halos of the two giant galaxies overlap, dynamical friction could act as a cosmic brake, reducing their relative orbital energy and potentially drawing them closer together. If the stellar disks overlap, an observer located within our solar system would witness an astonishing transformation of the night sky. The familiar, faint ribbon of the Milky Way could be joined by the enormous spiral figure of Andromeda, creating a vast and richly detailed luminous structure across much of the night sky. Despite the catastrophic scale of this encounter, a galactic collision is surprisingly non-destructive on an individual planetary level. The distance between individual stars within a galaxy is so immense that direct stellar collisions will be extraordinarily rare. The space between stars is vast. If our Sun were compressed to the size of a ping-pong ball in New York, the nearest star would be another ping-pong ball located hundreds of miles away in Atlanta. Therefore, if the two stellar disks pass through each other, nearly all of their hundreds of billions of stars would slip past one another, like ghost ships in the night, without physically colliding. However, the interstellar gas and dust clouds filling both galaxies could experience a radically different fate. Unlike stars, giant molecular clouds are vast, diffuse structures spanning hundreds of light-years across. If gas clouds from the Milky Way interact with those of Andromeda at high relative velocities, they could generate powerful shockwaves across parts of the merging systems. This gas compression could trigger an intense starburst event. Across both galaxies, many molecular clouds could collapse and form new stars, producing luminous emission nebulae, young star clusters, and bright blue massive stars. At the same time, gravitational tidal forces generated by the overlapping galactic masses could strongly warp both galaxies. Long tidal tails made of stars and gas might be drawn out of the main disks and extended far into intergalactic space. The spiral arms of the Milky Way and Andromeda could become distorted and reorganized into irregular streams of matter. If the galaxies remain gravitationally bound after an initial close passage, their cores could move apart for a time before approaching again. Repeated encounters and dynamical friction might then lead to a later merger, although the exact timing and outcome remain uncertain. In such a secondary phase, gravitational tidal friction will strip away the remaining orbital energy of the two galactic nuclei. The supermassive black hole at the center of Andromeda, with a mass of roughly 100 million suns, and our own Sagittarius A star, could gradually move toward the common center of a merging system. In a complete merger scenario, the two galaxies could eventually coalesce into a single structure. Their original spiral patterns would be strongly disrupted, and gravitational interactions could redistribute many stellar orbits into a thicker, more three-dimensional configuration. The resulting merger product might become a large elliptical or spheroidal galaxy, informally dubbed Milkomeda. It could appear smoother and more rounded than either parent galaxy, with hundreds of billions of stars and a reduced supply of cold gas. Star formation would likely slow over time, rather than ending instantly. At the center of a hypothetical Milkomeda, the supermassive black hole from Andromeda and Sagittarius A star could draw closer together and form a binary system. As their orbits shrank, they would radiate energy as low-frequency gravitational waves and distort the surrounding fabric of spacetime. The two black holes could eventually merge, creating a single supermassive black hole with a mass exceeding 100 million suns. Energy released during this process, together with possible activity from infalling gas, could heat or expel part of the remaining central gas and suppress future star formation. What will be the fate of our Sun and Earth during this cosmic merger? By the time a possible close encounter occurs several billion years from now, our Sun will be near the end of its main sequence lifespan. As the Sun ages, its core continuously contracts and heats up, causing its overall luminosity to increase by roughly 10% every billion years. Long before Andromeda makes its first pass, Earth's oceans will have boiled away, and its atmosphere will be stripped by intense solar radiation, rendering our planet a barren, hot rock. If a merger occurs, gravitational interactions could move the solar system away from its present galactic orbit and place it in a more distant region of the resulting galaxy. A direct collision with another star or the central black holes would remain extremely unlikely. In one possible deep-time future, tens of billions of years from now, a galaxy such as Milkomeda could stand as a solitary monument in the local universe. As dark energy accelerates the expansion of space, all other distant galaxy clusters will be pushed beyond our cosmic horizon, disappearing from view forever. To any distant future intelligence that might emerge on a planet orbiting a long-lived red dwarf within Milkomeda, their galaxy will appear as the entire observable universe, a single, sprawling elliptical island of aging stars surrounded by an endless dark void. The grand spiral arms of the Milky Way will be a distant memory, written only in the fundamental physical laws that built the universe. Our grand journey through the Milky Way reveals a cosmic home of breathtaking beauty, tremendous physical power, and profound complexity. From its chaotic origins after the Big Bang to the extreme gravity of Sagittarius A star, the brilliant birth of new suns in sweeping spiral arms, and the invisible scaffold of dark matter holding it all together, our galaxy is a magnificent evolving engine. We reside on a fragile rocky world, orbiting an ordinary star in a quiet suburban arm of this vast island universe. Yet, through science and human curiosity, we have unlocked the physical laws that govern hundreds of billions of suns across deep space and time. Our presence may be minuscule in scale, but our capacity to explore, measure, and understand the cosmos gives our existence extraordinary meaning. Thank you for traveling through the galaxy with us today. If you enjoyed this cosmic exploration, please consider liking this video, subscribing to the channel for more scientific journeys, and leaving a comment below sharing the location and time from which you are watching. Until next time, keep looking up at the stars.